I would like to continue talking constraint function construction. This is part 1 and part 2 video. This is part 2. If you are watching part 2 without watching part 1, please watch part 1 first. Otherwise, the material that I will cover on part 2, this video, may not make a lot of sense. You should watch part 1 first, then part 2. All right. At the end of the part 1 video for constraint function construction, I was talking about if you know how to connect two data points, then you can connect n data points in an iterative way. Now I would like to talk about another way. Another way to connect many points is to use higher order polynomials. So let's the final example on the part 1 video was we were connecting x1, x2, x4 four data points with each other. Now I would like to cover this I would like to connect them using a higher order polynomial. So in this case, since we have 4 points, we are going to have 8 constraints. First, at x1 of delta, you need to be y1. At x2, you need to be y2, so on and so forth. And I want to add some smoothness properties. The derivatives needs to be 0 as well. So we have 8 constraints and we need at least 8 weights in delta. In this case, I am going to consider this polynomial delta, which has a bias term w0, and then from 1 to 7 you have w1, w2, w3 all the way up to w4 multiplying x to the power of k. So total 7 weights and one more, you have 8 weights. I mentioned in the previous video, if you have 8 constraints, you need 8 weights. And if you would like to add also additional smoothness, 0 equals to delta prime prime at xi, so you are going to have 4 more constraints. In this case, you need to go from k1 to 11. You can do this as a homework exercise to deepen your knowledge. Right now, I just would like to focus on these 8 constraints. And you need to calculate delta prime, in this case, k, x, k minus 1, w. It is basically the derivative of delta with respect to x. Here is the procedure, right? I wrote in the previous videos these expressions explicitly, but as the order increases, let me mention the general recipe, what you need to do. First of all, apply these two equations to given constraints. What I mean by that, y1, for example, equals to delta x1 to satisfy this constraint, and in this case, you are going to use x1. To satisfy this constraint, 0 will be equal to this function evaluated at x1, which you need the x1 here. In this case, you are going to arrive 8 long equations, and I want you to arrange these equations into y equals to omega w form. Then you need to solve for w. Basically, w is omega inverse multiplied by y, and you have 8 constraints and 8 weights, which makes this 8 by 8, and you can, an inverse should be always exist in this case. That's why for the number of constraints given, you need to include that much weight such that you can invert omega matrix. All right, so let's connect these points. I am choosing the same 4 data points that I used in the last example of the part 1 video. This is how I construct omega, but right now they basically match with this process. Again, when you try to understand yourself, do it by hand. Take this, expand it, right? y1 equals to w0 plus w1x plus w2x to the power of 2 all the way up to w7x to the power of 7. Once you organize this, you are going to get these for the first equation, And for the second equation, you are going to, since you want their derivatives to be 0, you are going to get this part of the code, and you are grouping term. The first equation needs to be y1, y2, y3, y4, and delta primes needs to be equals to 0. So this basically represents y equals to omega multiplied by w. Solving this, and then this part of the code is just for plotting purposes. You are going to see that we have a nice fit that's shown here. Basically, here y not only passes through this point, but also y prime is 0. Here y prime at this point is 0, y prime also 0, and likewise in the last point as well. Now, I want to use exactly the same code, but I would like to change these points. I would like to connect 4 different set of points, right? I change these points in code to those. You can code this yourself. Only change is this. What you are going to see is that over this region, we kind of have a nice fit. But instead of going from here to there like this, we kind of have an overfitting issue. So I would like to talk with you how you can prevent overfitting, because overfitting can be problematic when you do path planning in controls, right? Or in robotic applications, if you want your robot to be at this position, then at this position, and at this position, moving from here to there, instead of going like this, why you should spend the energy of your robot going like this? This is kind of not desirable in controls applications. So how to prevent overfitting is an important issue. I would like to talk 2 ways. Way 1, always connect 2 points iteratively as described in part 1 of this lecture, meaning that connect this like this, then find another fit between these 2 points and find the third fit between these points. This will certainly prevent overfitting. You will have, first function here, the second function here, and the third function here. So you are connecting 3 functions and you are obtaining a composite function which satisfies all the constraints given. To understand this further, please watch the part 1 video. This will make crystal clear. Way 2 is for specifically to this overfitting issue is to consider this. Consider the case in the left figure. We do not have an overfitting issue for this region, basically from x between 0 and 5. This can be considered like a overfitting, but really it is not. It is on a ballpark. It is just nice. So I really personally, engineeringly, like the fitting in here. Now over x 0 to over and then between 5 and 10, I am talking about this region. Switch to another fit, basically in this case W0 and W1, W2, W3. Basically in this case we are connecting 2 points satisfying these constraints, meaning that one constraint we need to be here and there, 2 constraints, and derivatives needs to be 0, 2 more constraints. So we have 4 constraints to connect these 2 points. That's why we have 4 parameters, 1 and W1, W2, W3 coming from here. So use another fit. Let me illustrate this, these way 1 and way 2 in 2 examples. In the first MATLAB example, I am using way 1. I am iteratively connecting these 4 data points. And if you watched the part 1 video, this code is exactly the code that I used in the last example of the part 1 video. I am first connecting x1 and x2, x2 and x3, and finally x3 and x4. Then I am evaluating here. Basically, when x less than x2, basically over this region, I am running this code. Then when I'm in this region, I am running this piece, and finally I am plotting this piece. As you see here, smoothly I am transitioning from x1 to x2, x2 to x3, and then x3 to x4 that you see here. Do you see any overfit? No. This is the great approach that you can iteratively connect n number of points. Here I am connecting 4 points. Way 2 discusses that, well, I am happy about this fit, but I would like to modify this part to this. In this case, I am doing the fit like I did in the first example here. This part of the code that generates, sorry, not this one. The code that generates this is exactly this code. I am running this code as if I am connecting 4 points. But at the end, I am only using that fit when x is less than 5. I am just using this version of the fit. I am connecting all the data points, but then I am only using this half up to here. Then finally, to connect x3 and x4, what I mean by x3 and x4, actually literally x3, y3 and x3, x4, y4. I am connecting, I am defining another one here, and one xp is greater than 5, I am using that fit, right? I am doing the first fit, the second fit, and if you plot this, previously you had an issue like this, now it smoothly connects these 2 points. So I just described you 2 ways to avoid overfitting, and in my personal preference, I would like to connect iteratively all the points from 1 to 2, 2 to 3, 3 to 4, the way I described at the end of part 1. But if you would like to use higher order polynomial, of course you can use. If you see interesting overfitting cases that you should avoid, you can also consider way 2. All right, so finally, I would like to talk about composite function construction. We constructed functions, but let's say often in path planning or in control, now let me mention, if you would like to consider a Lyapunov function in general, right? You want it to be positive definite or satisfy these properties. Sometimes you may resort to composite function cases. Let me give you an example. Let's say you have a function that looks like this between 0 and x1, and you have another function that is looking like this, right? Let's say the first function, I would like to talk through an example, but you will understand. Let's say the first function over here is y equals to x to the power of 2. And the second function is y equals to e to the power of x. Now, similar to how we connect data points, we can also connect 2 or more functions with each other, and once we do that, we call them composite functions. So how we construct them, we call it composite function construction. In this case, you are looking for a function, delta, that connects these points by satisfying some properties. Let's say I would like to connect these points such that we satisfy these 4 constraints. First of all, delta that will connect these 2 points or these 2 functions at x1, delta of x1 will be x1 to the power of 2. I want that function to start exactly from this point, right? This first function, this is an open interval, is from 0 to open x1. So I am including x1 in this composite function such that this function must start from this point. Likewise, This function also includes x2, this is a closed point. So at basically y2, delta x2 needs to be e to the power of x2. This point is e to the power of x2, right? This point is x1 to the power of 2. You don't want to generate a function like this. This function needs to start where the first function ends, and this delta function should end where this third function starts. First of all, I would like to connect them smoothly such that, if you calculate y prime, it will be 2x. I want this delta function to have the same derivative at x1, 2x1. If you calculate d over dx ex, which will be itself, I also want when this delta function basically to have the same derivative at x2. You can consider this as a homework, but you can also have prime constraints. And I'm not going to do it right now. I am just considering delta prime. So I would like to connect smoothly these two functions. Since we have 4 constraints, I need to construct a delta that has 4 weights. And this is the delta prime, basically taking the derivative you obtain here, taking the derivative you obtain here, and this is here. Don't forget 4 constraints means 4 weights at least. I am doing the same thing for the connecting data points, but in this case I'm connecting functions with each other. All right, here is an example. These are the points that I would like to connect. This is the first function, x to the power of 2. This is e to the power of x, the third one. And this is the second function that I would like to find to connect these two functions. x1 and x2 is given. This is y1, this is y2. And these are the delta primes that are coming from these constraints, 2x1 and e to the power of x2, 2x1 e to the power of x2. And these are the omega functions that we construct. This is like similar. We are actually connecting 2 points again, but these points continuing from functions. And once you solve this for y, and then once you plot this for the first function, for the second function, and for the third function, you are going to see that we smoothly connect these two functions with each other. And this is how the final function looks like. Once again, as I mentioned, to further smoothen delta x, this connective function, constraints related with delta prime x1, delta prime x2 can be added. In this case, more ways needs to be used. 6 ways needs to be used. Please do this as a homework. And we use this technique for Lyapunov function construction for spatial needs. We use this in gradient descent, and we use this in many areas. And if not, just do it for fun. But at some point in your careers, if you are working with machine learning, robotic planning, path planning, Lyapunov functions, control theory, you are going to use this type of composite function construction, or in general constraint function construction, constraint function methods. All right, take care. If you like those, subscribe, like, turn notifications on. Take care.